Hello and welcome to a new session of physics. In today's session, we are going to continue the same topic from the last session that we were discussing, that is gravitation. I'm sure all of you would have come across a lot of interesting things about gravitation, a lot of interesting questions. We tried to answer a few in the last few sessions that we have done. In today's session, we are going to continue with with much more interesting derivations and also theory behind how gravity works and what are the effects of gravity, or what are the effects of gravitational force exerted by Earth on any other objects around it in a few different layers today. So before we get into today's session, let's quickly do a recap of what we are going to what we have done in our previous sessions, right? So before that, let's just quickly look at the topics that we are going to discuss today. We'll be discussing what do we mean by gravitational potential energy, gravitational potential, some very interesting things about escape velocity. What do we mean by escape velocity? If you have, I'm sure a lot of you have a lot of questions other than the 11.2 kilometers per second, the number in your head. We all grew up with a lot of confusion about escape speed or escape velocity. So we are going to discuss a bit about escape velocity of the Earth today specifically, and also a few facts and few fun things about Earth satellites. So what did we do in our last class, or in the last few sessions? We started with what do we mean by gravity. We differentiated gravitation from gravity, and we understood gravity is just a property which arises due to the mass of a given object. And also we understood that everything that has mass has gravity. Gravity is not only associated with the Earth, but it is associated with every single particle and every humongous star that has its own mass, right? So Johannes Kepler, who laid the foundation for modern astronomy, basically proposed three laws of planetary motion, which we are using even today, and they are applicable empirically, right? So laws of orbit is the first one of them. What does it state? It states that every planet around the sun orbits around the sun in an elliptical orbit but not circular, as opposed to the theory which was accepted before Johannes Kepler, right? So the next one is laws of areas. Laws of areas basically states that if the imaginary line joining the planet and the sun, which is at one of the foci of the elliptical orbit that the planet is revolving around, is basically it sweeps, this imaginary line sweeps equal areas in equal intervals of time. So if we are able to measure the area swept by this imaginary line joining the sun and one of the planets in the solar system at equal intervals of time, the number or the ratio that we get for the area and the time period will be constant. And law of periods states that the square of the time period, or the revolutionary time period, that is period of revolution that is taken by each of these planets, is directly proportional to the cube of the distance between the planet, cube of the semi-major axis of the elliptical path, it is elliptical orbit that it is orbiting in, right? We also understood what holds the universe. By now you all must be really clear that without gravity the universe would not function. Not only the world, but the universe would not function the way it does today, right? So what is holding the universe? Gravitational force of attraction between every object in the universe is exerted on every other object in the universe. That is what is holding us today. And how is this force measured, or how do we quantify this force? No, I mean, we don't have to worry about it. Newton has done a tremendous job in contributing to this particular law or particular field as such, by giving the universal law of gravitation, which basically states, or which basically allows us to quantify this gravitational force of attraction between any two given objects or masses, right? So it is given by this equation, F is equal to g m1 m2 divided by r square or d square, whatever you want to represent the distance between these two masses as, right? Where g is the gravitational constant. Again, this is a universal gravitational constant, which is a constant which remains the same everywhere you go in the universe, no matter what circumstance, no matter what time you go. Again, time is relative when we think about it, right? So we also did the dimensional formula for g. We understood how gravitational force of attraction between any two objects is conservative in nature by proving the vector form of it, correct? Yes. So we also understood what do we mean by acceleration due to gravity. What do we mean by acceleration due to gravity is one of the important questions that you have to ask yourselves, and also understand the difference between gravity and acceleration due to gravity and gravitational force. I understand if there is a little confusion here, but please bear in your minds that never use the word gravity instead of acceleration due to gravity. I have seen, we have come across a lot of people who use 9.8 meters per second square as, oh, gravity. No, it is not gravity. It is acceleration due to gravity. Both the parameters or both the quantities are very, very, very different. Here, acceleration due to gravity arises because of the force exerted due to an object's gravity, right? So gravitation or gravitational force can be used interchangeably, but not gravity and gravitation, or not gravity and acceleration due to gravity. So acceleration due to gravity is the acceleration produced in a body which is falling freely under the influence of gravitational force of a given planet. It could be Earth, it could be anything else, right? Or it could be a satellite like Moon as well. They might have lesser amount of gravity and hence they produce lesser amount of gravitation, but nonetheless they do have their own gravity. So what do we mean by gravitational acceleration due to gravity? How can we define it? We have already done it. It is the acceleration produced in an object due to the due to the influence of gravitational force of a given planet or the Earth, or it could be a satellite as well. So what do we mean by free fall? We also defined free fall, right? Whenever an object falls under the influence of gravitational force of attraction of the Earth alone, then we call this as a free fall. That means we are not taking into consideration any of the other forces acting on this object. Obviously, if we drop a feather and a heavier object such as an iron ball or a watermelon, obviously the rate at which they would reach the ground or they would fall towards the ground would be different because of the air resistance. That is exactly why you cannot actually say that when you actually look at the feather falling and a heavier object falling towards the ground, we always tend to say that, okay, heavier objects fall towards the ground faster, but the lighter objects take a while, and hence their acceleration due to gravity is different. But it is not the case. In the absence of every other force, if it is only the gravitational force that is acting on an object, it could be heavy, it could be light, it could be large, it could be small, it does not matter. We have discussed in length and details that the mass or size or volume of an object which is falling freely into the influence of gravitational force of the Earth does not actually affect the value of acceleration due to gravity of a given object under free fall, right? So this basically was first proved and proposed by Galileo. Acceleration due to gravity on an average is taken to be 9.8 meters per second square all over the Earth. Why is it taken to be an average value? Because it is maximum. It varies. The value of acceleration due to gravity varies with height and with depth and also with latitude. That is what we have realized, and we have discussed this, correct? So variation of acceleration due to gravity, or first general equation for acceleration due to gravity, is given by G is equal to capital G m divided by r square, where r and m are the radius and mass of the Earth, respectively. And how does it vary? G basically varies or fall. The value of G goes on decreasing as and when we move away from the center of the earth, and also it falls as and when we go deeper and deeper into the earth. We deduced the both the equations for for the variation of acceleration due to gravity. We also understood how it varies with the latitude, right? Because our earth is not a perfect sphere, it is a oblate spheroid, right? So because of this shape of the earth, the polar radius is lesser than that of the equatorial radius, because of there is an equatorial bulge, and there is a flattening at the poles of the earth, and hence the polar radius is not exactly equal to the equatorial radius, while the equatorial radius is slightly greater than that of the polar radius, and hence this creates the difference or the variation between the acceleration due to gravity at equatorial regions and when we go to the polar regions. So as you know, on a lighter note, if we immediately want to feel good about our weight, let's go to the equator, because we'll weigh lesser over there. Now, variation of G with latitude is given by G dash is equal to G minus omega square R cos square theta, where theta is the latitude and omega is the angular velocity, or the angular velocity of the earth. So where G dash is the apparent value of acceleration due to gravity in the absence of rotation of the earth at that given latitude, where G is the true value of gravity at that given latitude in the absence of rotation of the earth. I'm sorry if I've interchanged it while reading it, but G dash is the apparent value of acceleration due to gravity at the latitude due to the rotation of the earth, in the presence of the rotation of the earth, that is where we consider G dash as. That is the reason we have taken into consideration the angular velocity omega of the earth, and whereas G is the acceleration due to gravity at the same latitude but in the absence of rotation of the earth, right? Now let's solve one or two practice questions, very simple ones. If the value of G at a certain depth from the surface of the earth is equal to 25% of that at its surface, then calculate the acceleration due to gravity at this point. Now we just now have discussed, or we just now recalled, what are the equations that we derived for variations of acceleration due to gravity. So here, if you recall, we have this equation. This is for the variation of acceleration due to gravity with altitude, and this here is the variation of acceleration due to gravity with depth, right? Pretty simple, as we can, as you can see here. If you want us to go through the question again, if the value of G at a certain depth from the surface of the earth is equal to 25% of that at the surface, that is at normal G, then calculate the acceleration due to gravity at this point. So they are asking what will be, at what depth the acceleration due to gravity is 25%, right? So the options are 1200, 1200 kilometers, 4000 kilometers, 3600 kilometers, 4800 kilometers. Now how do we do this? Now what do we know of here? We know that the information that they have given us here is G dash, that is at a depth, at a certain depth, where acceleration due to gravity is 25% of that value on the surface of the earth. So G dash is equal to G into 25 divided by 100. Why? Because it is 25%. So this would be is equal to G dash is equal to G divided by 4. Now we have this value of G, and we know that for a certain depth D, G dash can be given by G dash is equal to G into 1 minus D divided by capital R, where R is the radius of the earth, which is given by 6,400 kilometers approximately, right? Now with this equation, can we calculate the value of G dash here? Most definitely yes. So if we are to calculate the value of g dash, it is very simple. G divided by 4 would give you the value directly. And if we are to calculate the distance at which, or depth at which, g loses or g reduces to 25% of its original value at the surface, then we are supposed to calculate the depth of it, right? So let's do that. So g dash is equal to g divided by 4, and hence in this equation, in the above equation that we wrote in the previous screen, let me write it again. G dash is equal to g into 1 minus d divided by r. We know the value of r, correct? So can we not substitute g divided by 4 for g dash? Most definitely yes. So this basically becomes a convenience for us in order to reduce the equation for d here, the depth, correct? So on simplifying, what do we get? The like terms get cancelled. We get 1 divided by 4 is equal to r minus d divided by r, correct? Yes. So we have, on simplifying, what do we get? R is equal to 4r minus d, or minus 4d. Therefore 3r is equal to 4 into d, and we have final equation d is equal to 3 divided by 4 into radius, that is 3 at depth, or at a distance from the center which is equal to 3/4 of the radius of the earth. The acceleration due to gravity is equal to 25% of the acceleration due to gravity at the surface, that is g divided by 4. So what would the distance be? Remember, we have the options here. So 3 divided by 4 into r basically gives us, let me do it here, d is equal to 3 divided by 4 into 6,400 kilometers. So on simplifying, what do we get? We get this as 16 3s are 4,800 kilometers is the depth at which the g value varies with or reduces by 25%, right? 25% of that at the surface of the earth. So we can most definitely calculate that value as well. All we need to do is divide 9.8 meters per second square by 4, right? Next question. So find the value of acceleration due to gravity at a height 3,200 kilometers above the surface of the earth and at a depth 8 kilometers below the surface of the earth. It's very simple and straightforward. So believe me, this is a question that was given in one of the previous year question papers. If you get questions like this which is of direct substitution, all you need to do is remember the formula or equation for these variations of g, correct? They have given you all the information that is required. They have given you the radius, they have given you the value of g, that is g at the surface itself. So how do we do this? First one, the part A of this problem, at a height 3,200 kilometers above the surface of the earth. How do we do this? For this, we need to know the formula for variation in g with the altitude, correct? So for altitude h, g dash will be is equal to g into r divided by r plus h, or just 1 plus r by h. Correct? Yes. So using this equation, if we simplify, we know all the values here. We know the value of r, we know the value of h, we know the value of g. So what is r? 6,400 into 10 raised to 3 divided by y, the conversion factor, because 9.8 meters per second square is in SI units. You need to be careful about it. So r is again 6,400 plus what is the value of h at a height 3,200, a common factor, that is 10 raised to plus 3. We don't need to now you see why it does not have too much of significance, because there are like terms in the denominator and numerator, they get cancelled. So we get g dash as what will be the value of g dash? It will be 4.36 meters per second square on simplifying this particular term here, right? All right. Now, the second part of it, at a depth of 8 kilometers below the surface of the earth. Again, using the equation that we used in the previous question, that is g dash is equal to g into 1 minus d divided by r. This is what we get, correct? Sometimes there will be questions like, okay, what will be the value of g at an altitude 3,200 kilometers above the surface of the earth, and also what will be the value of g at the same depth of that as the altitude below the surface of the earth. Then you use these two equations and substitute the same way, and you get the answer, right? So here on substituting, what do we get? We need to substitute 8 here and divide it by 6,400, and we have all the other information that we need to solve this question. I hope you get this. It's a very simple and straightforward question, right? So moving on. Now, when it comes to any of the objects which is raised above the surface of the earth against the influence of Earth's gravitational force, we need to do some amount of work, correct? But when it comes to and larger the mass of the object, and we feel this, the object is heavier and heavier, correct? So if I need to lift a 4 kilogram iron block, and if I need to lift a feather, which would be easier? Obviously, I will lift the feather much easier than that I would do when it comes to the 4 kilogram iron block, correct? Why is that? Because the gravitational pull that is in the form of weight of this object is much higher when it comes to 4 kilogram mass, correct? Mass here is a key quantity which basically determines the amount of gravitational pull that is acting on a given object. So what do we mean by weight, and how is it different from mass? You've studied this in your high school. Mass is just the amount of matter present in the object, whereas the weight is a form of force. It is the amount of gravitational force that is that is exerted by the Earth's gravity on an object due to its own mass, correct? Yes. So in that case, how do we write this as? W is equal to mass into acceleration due to gravity, g. So as you can see here, general equation of force is what? F is equal to m into a, correct? Yes. So mass into acceleration basically gives you the force, and hence weight is a form of force, whereas mass is just the amount of matter contained in an object. And also mass is a scalar quantity, whereas weight is a vector quantity which is always directed towards vertically downwards, correct? Now when it comes to mass, we can categorize, or we can say that it is of two forms. One is the inertial mass, and another is the gravitational mass. While the number, that is the quantity, when we say, okay, 4 kilogram is a mass of an object, the 4 kilogram remains the same when it comes to inertial mass and the gravitational mass of the same object. But those two things, inertial and gravitational masses or mass of a given object, tell us two different stories. What are those things and how are they different? So inertial and gravitational mass of an object might be the same number, but they tell us two different things about this object. So how do we differentiate this? As we all understand, gravitational mass or gravitational force of a given exerted on a given object due to another object is basically given by universal gravitational law, correct? So as you can see here in this equation, m1 and m2 that are considered for these two objects, or for this particular equation, are termed as gravitational masses of these two objects. Here, when it comes to F is equal to m into a, so when I write the general equation for the force exerted on a given object of mass m, whereas this force produces an acceleration a, depends on this mass also, correct? Yes, larger the amount of mass, if we apply smaller force, it produces a very small amount of acceleration. But if the same amount of force is exerted on a smaller mass, it produces a larger acceleration. That's how it works. Correct. So here, even if I take the same m1, if I have, if an external force is applied onto it, that mass here represents the inertial mass. Correct? Yes. So how do we differentiate, or how do we define these two masses? Gravitational mass is the mass of the object that is measured in terms of gravitational force, that it can exert on the other objects. So how is gravity coming into picture for a given object? It comes into picture because of the mass. Larger the object, larger is the mass, and hence higher is the amount of gravity possessed by it. Correct? Yes. So when we look at the sun and when we compare it to the mass of the earth, it is humongous, right? It is very, very, very large. So the gravity possessed by the sun is very, very large in nature. However, when we calculate the gravitational force of attraction between these two objects, it does not matter if one object is larger and another object is smaller. One object has, higher mass and the other object has lower mass. That's because the gravitational force of attraction between these two objects depends on the product of the two masses and not on the individual mass. Correct? So, how do we differentiate gravitational mass from inertial mass? Inertial mass is the regular mass, or which can be measured under any of the influence of any of the force. But when it comes to gravitational mass basically gives us the measure of, or it can be measured in terms of the gravitational force of attraction that an object can exert on the other object. Right? So how do we define inertial mass as opposed to it? It can be termed as the measure of the resistance to any change in the state of object measured under any force. Not only under gravitational force, but any other external force. Right? So these two are, different forms of masses, or two masses that an object can have. Of course, when we say mass of the object is 4 kilograms, it basically is the measure of both gravitational and inertial mass. Though the number is the same, these two masses, or these two forms of masses, tell us two different stories. It's very important to understand the fundamental difference. So because of this, because of the gravitational mass of a given object, it possesses a certain kind of energy. We have studied this in work power and energy. We have studied this in your high school as well. There are different forms of energy, or when it comes to mechanical energy, there are only two types or two forms of it. What are those? Kinetic and potential energy. When it comes to potential energy, we always talk about two forms of potential energy, or two types of potential energy an object can possess. So in general, potential energy is nothing but the energy possessed by the objects because of a certain position. Correct? So when, in case of a bow and an arrow, when I pull the arrow backwards, I am doing certain amount of work by exerting some amount of muscular force onto that arrow and displacing it from its original position. Correct? So whatever the amount of work that I'm doing to displace that arrow to bring it to a certain position, that work will be stored as potential energy at this position. Correct? Yes. So when I let go of the arrow, if I pull it more and more backwards and let it go, what happens? The amount of velocity that it gains because of the position that we pulled it to is basically converted into kinetic energy. Again, this is also a form of work done in order to give it a certain amount of velocity. So how do we differentiate between the different forms of potential energy? Here, the elasticity came into picture. Correct? I could pull the arrow because of the elasticity of the bow, and I mounted that arrow to that elastic band, whatever the bow has. Correct? So because of the elasticity and the position which it was pulled to, it had a certain amount of potential energy. But in case of an object wherein I am picking up an object and if I say, for example, I'm picking up a book from the table and I'm placing it at the top shelf, what happens to it? Will it not possess any kind of energy? Is there any amount of work not done onto it just because there is no elasticity involved? Of course not. There is a lot of work that is involved in picking up the book from one position and keeping it on the top shelf, because it is the work done against the influence of gravitational force of the earth as such. Correct? So how do we define gravitational potential energy? Gravitational potential energy is the energy possessed by an object, when a certain amount of work is done to bring it to a certain height against the influence of gravity of the earth or in another gravitational field. So for this we have an equation, or how do we quantify it? It is usually represented as capital U, and its equation is negative G capital M into M divided by R. Now let's talk about the significance of the negative sign here. It is not, I assure you, it is not a very common thing that we come across. We will talk about it in a while. Now let's derive this equation from a very, very simple work done is equal to the potential energy concept, right? Now consider a mass which is kept at point P here, which is at a distance x from the center of the earth. Alright, now we know that this distance to the surface from the center of the earth is nothing but the radius of the earth, correct? Now this object, let's say it has mass m, right? Now what you can start with is consider an object of mass m placed at a distance x from the center of the earth. Now we know that the radius of the earth is represented as r and the mass of the earth is represented as capital M. So how do we do this? Now the gravitational potential energy possessed by this object is nothing but the amount of work done on this object to raise it to a height through a distance x, correct? Yes. So let's say the force exerted or force acting on this object can be given by universal law of gravitation, that is F is equal to G M capital M divided by R square. Let's keep this as equation 1. Now in order to raise it through a certain height from the center to that point P, we have gone through the distance, the amount of work done, or the force had to do push this object through a distance x, right? Now let's consider the small amount of work done, that is dW is equal to small amount of work done by this force to bring it or to move the object through a certain small distance dx can be given by dW is equal to force into displacement, correct? Yes. Now if at all, how do we define gravitational potential or gravitational potential energy? We are bringing an object from a point of infinity to a certain point r, or wherever it is desired, correct? Yes. So how do we calculate the total amount of work done in this process? We do the integration, or we integrate the both the sides of the equation, we get the total amount of work done, correct? Now if F is the force used to move the body from, or move the body of mass m through a distance, small distance dx, then dW is equal to F into dx is the small amount of work done, correct? Yes. Now therefore integrating, what do we get? The total amount of work done, W, is equal to, from where to where? We have to know the limits also, correct? I'm sure all of you would have come across simple integration techniques by now. We have used it in multiple derivations in the previous sessions also. So here we are bringing the bringing the object of mass m from point of infinity to r, correct? Yes. So integrating it from or between the limits infinity to r, we have the equation f into dx. So x being the variable here, because x is the distance, any distance x between the limits infinity and r. So we substitute, what do we substitute for? We substitute for f here. So infinity to r, g capital M small m divided by r square into dx, correct? So with this equation, let me write the equation again. Infinity to r, instead of f, we substituted for f, g, m divided by r square into dx. We have here again, instead of r, we are basically supposed to calculate it for x, right? So let's go back and correct this. Here what are we doing? We are calculating the amount of work done in bringing an object through a distance x, correct? So it would not be r square here, it would be x square instead of r square. So this is the general equation for the force exerted on an object on the surface of the earth, correct? So if at all the same force had to be used to move the object through a distance x, then this equation would become f is equal to gmm divided by x square, correct? Yes, that is what we have used here. Moving on, we have, instead of r, we need to write this as x square, because the here we are taking the distance as the variable and distance is taken to be as x, correct? So since g capital M small m, all of these things are not variables, they are all constant. So I take that out of the integration sign. What are we left with? Gm capital M integration of 1 divided by x square between the limits infinity to r, correct? We are left with this. Now we know that for simple identities, simple integration identities, we know that any integration of x raised to n can be given by x raised to n plus 1 divided by n plus 1. Now here we have 1 divided by x square, so can we write this in the form of x raised to n? Of course we can. We can write this as x raised to minus 2. This gives us, what do we get? We get this as x raised to minus 2 plus 1 divided by negative 2 plus 1, correct? So we get the integration of x raised to minus 2 as negative 1 divided by x, right? So substituting that here, gmm into negative 1 divided by x between the limits infinity to r, we take the negative sign outside, we get g capital M small m into, what do we get? 1 divided by r minus 1 divided by infinity. So we all know that we will be left with only 1 divided by r, because 1 divided by infinity is basically 0. So capital Gm m divided by r is what we get the equation as. Not capital R, will be small r, where r is the distance through which we are basically moving from a point of infinity to any distance r from the center of the earth, correct? Now by definition, this amount of work done is equal to what? This by definition is equal to the potential energy, or gravitational potential energy to be precise, is equal to the amount of work done on an object in moving it from a point of infinity through a certain distance r in a gravitational field of another object. What is the another object here? It is the earth, correct? So this by definition will be is equal to U, which is the representation for the gravitational potential energy. It is given by negative capital G small m into capital M divided by R is the equation that we wanted to deduce for the gravitational potential energy of a given object placed in the gravitational field of another object, right? So with this, now let's define the gravitational potential. So I'm sure you in high school you would have studied electric potential and electric potential difference, right? So what was the difference over there? Electric potential is nothing but the amount of work done. Both are work done in that case, correct? So electric potential was the amount of work done in bringing an object from point of infinity to a desired point, correct? Whereas electric potential difference was within a very small distance or within a circuit, to be precise. Similarly here, how do we define gravitational potential? Gravitational potential energy or energy per unit mass is what is gravitational potential. So gravitational potential at a point in the gravitational field is the amount of work done in bringing a unit mass. Please remember, this basically is concerned or associated with the unit mass when it comes to gravitational potential alone, okay? Whereas gravitational potential energy is for any amount of mass which is taken to be a small m in the previous equation, right? Bringing a unit mass from infinity to that point in the gravitational field of another object. So with this, we know that U is equal to, the gravitational potential energy is equal to negative G capital M into M divided by R, right? So this basically, if the unit mass is taken to be small m, then V is equal to U divided by M. This will be is equal to negative G M divided by R. This is the general equation for the gravitational potential at a given point in the gravitational field. All right. Now, with this, we have understood that if at all there is a certain object of mass m which has to be moved through a distance against the influence of gravity, or against the in a gravitational field, it takes a lot of work to be done, correct? Basically, what is kinetic energy or what is potential energy? How do we define it? By definition, it starts from the amount of work done on an object in order to give it a certain kind of velocity. We associate that with the kinetic energy, whereas if it is by the virtue of the position, it could be due to its elasticity or due to a certain height, then we call that as potential energy. It could be of two forms, gravitational and elastic. Correct? Now, when we say the object has to leave or object has to escape the gravitational force exerted by a certain other object, then what do we do? Or then how much amount of work that needs to be done, or what exactly is the velocity that needs to be given to that object in order to escape the gravitational field of another object? Let's look at that. But before that, let's not forget the significance of negative sign here in this equation. U is equal to negative GMM divided by R. Now, what we usually come across as negative, in any of the physics equations, such as if we say work done is negative, it basically means there is a direction, that is the force and the displacement are in different directions. But here it is not the same case. It does not represent the work done against the influence of gravity. It basically says that it is brought, the amount of work done is brought from a point of infinity to a desired point. It is not the amount of work done against the influence of gravity. It is not the case here. All right, it's a very important difference, and it is a good point to remember. Now, as we were discussing, can we escape the gravitation of a given planet, or it could be a satellite, or it could be a star as well? Can we? Of course we can, but it takes a tremendous amount of velocity to escape, escape the gravitational field of a given planet. If it is a planet like Jupiter, it takes a lot of velocity to be given. In order for that velocity to be gained by an object, we need to apply a lot of force, right? So let's understand what do we mean by this velocity. So what is the velocity required to escape the gravity of a planet or gravitational field of a planet? We call this as the escape velocity. Now, getting anything into the deep space beyond the Earth's gravitational field or Earth's orbit from the surface of the Earth, it takes the same amount of force, and hence the amount of velocity required for any object to escape the Earth's gravitational field is exactly the same. It could be the Falcon Heavy, that was launched by Elon Musk's SpaceX. It could be a roadster. Again, he sent the roadster, with a dummy, a very cherry red Tesla car into the space, and also even a baseball, which is very small in compared to the other two objects here, right? They all require the same amount of launch force, and hence the same amount of velocity with which they need to be launched upwards into the space in order to escape the Earth's velocity. So this is known as the escape speed or escape velocity. So it is, how do we define it? It is the minimum speed or velocity with which a body must be thrown upwards in order that it just escapes. It is just enough to escape the Earth's gravitational pull. So how do we deduce an equation for this? Again, when it comes to giving a certain amount of velocity to a given object, we need to do certain amount of work, correct? Yes. So while we are at it, while we are doing this certain amount of work, only if at all a particular object gains kinetic energy, that basically means there is a certain amount of work that is done on that object in order to give it that value of velocity, right? So how do we calculate the escape velocity, or how do we deduce an equation for this escape velocity, or the minimum amount of velocity that is required for an object which is launched upwards to into the space, escaping the Earth's gravitational pull? Let's do that. Now we know that if at all there is an object which is kept at a point A and it is of mass m, we all start again with the same equation, that is universal law of gravitation. If there is an object which is kept at a certain distance r, from the surface of the Earth, we have the force that is exerted, F is equal to G m, capital M, divided by r square, where r is the radius of the Earth here. So if it is kept on the surface, of course, this will be the equation, or the equation for the force exerted. So we are launching it from the surface of the Earth. That is why we have taken the distance as the radius of the Earth. Now, if at all it is from a certain distance above the surface of the Earth or anywhere in general, we take this as x, and hence we have another equation. So even then the force is given by the similar equation, but only the distance changes, right? So now we need to do a certain amount of work on this particular object in order to launch this object from the surface of the Earth into the space. That means we are to calculate the work done on this object to launch it from a point of radius of the surface of the Earth into the space, that is into an infinite distance, right? So what is the small amount of work done on this object by the force? So it would be F into small distance dx, correct? Now in order to get the total amount of force done, or work done to launch this object of mass m from a distance or from the surface of the earth to infinity, into the space, right? So we integrated from capital R to infinity, right? And we substitute for the force here, gmm divided by x square into dx, x being the variable here, correct? Yes. Now let's write down the equation once again so that we don't forget, or I don't forget. Not infinity, it is from the surface of the earth of radius r to infinity, and hence g capital M divided by x square into dx. So therefore w is equal to, what do we have here? We take the constants out of the integral sign, and hence we have r to infinity 1 divided by x square into dx, right? Using the similar technique that we used in the previous derivation. So we have integration of 1 divided by x square giving us negative 1 divided by x, correct? Yes. So w is equal to g capital M small m into, what do we have now? Negative 1 divided by infinity minus 1 divided by r, right? Yes, but we are not to forget this negative sign here, right? So what do we get? We can, not 1 minus infinity or 1 divided by infinity, we take the negative sign outwards. So we have 1 divided by infinity minus 1 divided by r. Therefore, w is equal to minus gmm into, so 1 divided by infinity, of course we don't consider that, into 1 minus 1 divided by r. We get w is equal to g capital M small m divided by r as the work done. So this, let this be equation 3, right? So let me write the equations on this side here. Now by definition we know that this particular amount of work done is equal to the amount of kinetic energy possessed by the object which starts moving after the amount of after this work is done on it, correct? Yes. So let's say this this gives it a velocity of v, which is the representation for escape velocity. So the amount of kinetic energy gained by it will be is equal to half mve square is equal to g capital M small m divided by r, right? So solving it for ve, what do we get? We get this as 2g capital M small m divided by m into r. Of course, if you if there are like terms on these two on the either side of the equation, so we don't need to write small m anymore at all. So we get this equation. So generally we can represent the escape velocity as 2 into gm divided by r as the general equation. So furthermore we know that g is equal to acceleration due to gravity, g is equal to capital G m divided by r square, correct? So can we not use this in order to solve or get a simpler equation for velocity here, the escape velocity? So of course we can solve this for the term g into m. We get small g into r square. Therefore substituting that, what do we get here? ve is equal to under root 2 into, instead of gm, what do I have? G r square divided by r. Therefore I get the final equation as ve is equal to, let me just write it here, ve is equal to under root 2 into g into r as the final equation, right? So this is the general equation for escape velocity, or this is the amount of velocity that is bare minimum, this is the amount of velocity required at least this amount of velocity is required for an object of mass m to be, or any of the object to escape the Earth's gravitation. Now, we know the value of g here, that is 9.8 meters per second square, and r is the radius of the Earth, approximately 6,400 kilometers, or 6,400 into 10 raised to 3 meters here. So if we calculate all of these and simplify, and we get the value of VE as 11.2 meters per second as the escape velocity for the Earth's surface. From the Earth's surface, if at all an object has to escape the Earth's gravitational field completely, then it has to be launched at a speed of 11.2 meters per second. So similarly, if at all there are, if you would like to know few other, planets or satellites escape velocity, here are few. For if at all we have to escape the moon's gravitational pull, we have to escape it with a velocity of 2.3 kilometers per second. It's not much. Mercury, it is 4.28. Earth, as we said, 11.2. Look at Sun and Jupiter. It is a whopping 618 kilometers per second is the amount of velocity with which is required just to escape the Earth's, Sun's gravitational field. And Jupiter, it is 60 kilometers per second. So with this, we come to our satellites. So what are satellites? Satellites are not as large as the planets which revolve around the star, but satellites are revolving around the planets in turn, right? So planet and along with its satellites, basically as a system, it revolves around its own star. For example, Jupiter and the Galilean satellites, and the 4 Galilean satellites. Why is it called as Galilean satellites? Because Galileo discovered them. So Callisto, Io, Europa, and Ganymede are the 4 Galilean satellites that are very prominent when you look through a telescope and you observe Jupiter. So of course Jupiter has many more other satellites, but as a system as a whole, which basically this planet holds all of these tiny satellites together, and as a system it basically revolves around the star, that is our sun. So what are these satellites, or how can we define them? These are the celestial bodies that revolve around a planet, and together as a system they revolve around the star, which is our sun. So how many satellites do we have? As in, how many satellites does the Earth has? Of course, it's only one, the natural satellite. It is only one, that is the moon, what we call this as moon. Whereas we have thousands and thousands of artificial satellites that we have launched into different orbits for different purposes, right? There is on a lighter note, we have not only created pollution on the Earth, we have also polluted this space around the Earth by launching many satellites than it is required actually. But what is the purpose of launching these artificial satellites? You name it, the purpose is, or you name it, we use satellite for these purposes. When we browse something at the click of a button, what do we use? We use satellite communication. When you switch on your television and watch some program which is being telecasted, of course, again, satellite. For military purposes, defense purposes, for telecommunication, the internet, web, the World Wide Web. And if I'm able to sit here and if I'm able to talk to a person who's on the other side of the globe, say in South Pole, North Pole, anywhere, one click of a button, we can do that, right? So how is this possible? If we are given very accurate weather predictions, today it's going to rain, today it'll be sunny, tomorrow it's going to rain more heavily, or in a week there'll be a cyclone hitting us. All of these predictions, how is it possible? Again, it is because of the artificial satellites which are revolving around in different orbits around the Earth. So there are different kinds of satellites which are launched at different levels or different altitudes from the Earth's surface, which are for different purposes. So depending on the purpose for which these artificial satellites are used, their orbits are basically decided. They are all revolving around the Earth in circular orbits, and the altitude at which they are launched is decided based on the purpose of that satellite launching, right? So more on this in our next session, and we will learn what are the different kinds of satellites that we have, and how these satellites are launched into their particular orbits, what is the orbital speed with which they are moving around the Earth, and what is the significance of orbital speed of these satellites, and also the time period with which they are revolving around the Earth. Many such interesting stuff we will be discussing in our next session. I hope today's session was fulfilling, and before we end the session, let's just quickly recap what did we do in this session. We understood what do we mean by gravitational potential. We understood gravitational potential energy, how are they different from each other. We derived the equation for the gravitational potential energy possessed by an object which is at a certain distance from the Earth's surface. And also we understood what do we mean by escape velocity, how much is the escape velocity that is required for an object, that is bare minimum velocity that is required for an object just to escape the Earth's gravitational field. We also looked at different escape velocities of few other planets and our moon as well. We understood what do we mean by artificial and natural satellites, why do we have them, and we will discuss more on this artificial satellites and their orbital orbital speed, and we'll also understand what do we mean by weightlessness, which is a very interesting topic again in our next session. Until then, bye-bye.